um, of foods at this university. He has published more than 100 papers and several book chapters, mainly in the area of chemical and physical properties and behavior of food and food components in simple and complex model systems. His current research projects are associated with phase transitions and structural organization of lipids and their application in vegetable oil processing and the development of new lipid-based trans-free food products. Dr. Toro-Vazquez is an associated editor of the Journal of the American Oil Chemists Society, reviewer in several scientific journals, and he is an active member of the Mexican Academy of Science and the American Oil Chemists Society, the Institute of Food Technology, and he has also been awarded the maximum level of recognition by the National Council of Science and Technology of Mexico. Dr. Toro-Vazquez also works as a consultant of several international food and cosmetic companies associated with the production of lipid-based products such as Bimbo, Campbell's, Cargill, Ragasa, Palsgard, among others. The Mexican Council for Research and Technology has awarded him twice with the National Award in Food Science and Technology, and in 2017 he received the Timothy L. Mounts Award from the American Oil Chemists Society in the US. So it is a pleasure for me to introduce to all of you, Dr. Toro, welcome, and thank you again for your time and for this presentation. Please, before we start, remember to mute your microphone during the presentation, and if you have any questions through it, you can write them or in the chat or so that you don't forget them, and at the end you can ask them directly to our speaker, or I can also read them out loud for you. Thank you, Dr. Toro.
Thank you very much, Viridiana. And good morning, good afternoon, good evening, or good night. First of all, let me thank to this very pleasant invitation that I received from the president of the International Society of Food Engineering, Dr. Jorge F, which is a full professor at the Tecnológico de Monterrey here in Mexico. It's an honor to be here with you to share some of the information in this field of lipids. Nowadays we are experiencing drastic change in the kind and type of edible fats that are used in different food systems that require the nutritional and functional properties associated with fats. And it will be a pleasure for me to share some of the results generated in my laboratory and also in collaboration with other groups in different universities in the United States, Canada, and Belgium mainly. And let me start by closing my video. I have some problems with my internet connection, so I don't want that you stop seeing my presentation or stop hearing me. So I'm gonna stop my video and start my presentation with, as you can see here, the title, Molecular Self-Assembly and the Development of a New Generation of Edible Fats. And here is the general outline, that I'm going to present. We are going to start with discussing some of the uses of vegetable oil in food systems, obviously going through to the use of partially hydrogenated vegetable oil, which has a high content of trans fatty acids, and start introducing the general concepts of molecular self-assembly, the difference between organogels and oleogels. And from there, we are going to start sharing some of the data generated in my laboratory that deal with the chemical and physical variables that determine most of the characteristics associated with molecular self-assembly in vegetable oils. The studies associated with molecular self-assembly are very early, probably less than 10 to 50 years. So we need to know more about these molecules and how they assemble, how they provide the functional properties that they require, because this is the new alternative to generate a new generation of fats. We're going to see the effects of different chemical structures and functional groups in this self-assembly, and the effects of mass and energy transfers in this phenomenon. Then I'm going to start finishing my talk with the use of vegetable waxes in the development of edible oleogels and their use in food systems, and what we expect of future. And what I call future actually is these current days in the use of different approaches to structure vegetable oils and to develop this new generation of fats. And saying this, I'm going to start reminding you what is the main components of vegetable oils. As you may recall, vegetable oils are constituted essentially by triglycerides, which are esters of glycerol with different fatty acids. The fatty acids may be saturated and unsaturated. And these components, which are in about 95, 98% in the vegetable oils, provide the liquid characteristics of the vegetable oils, mainly associated with the extent of unsaturation of the fatty acids. And because of that, most of the uses of the vegetable oils are restricted to its use as frying oil, and in some cases like olive oil, sesame oil that have a very bland flavor. They are used in salad dressings, and other than tropical oils like coconut oil, like rice oil, like cocoa oil, which are plastic, semi-solid at room temperature, we have to hydrogenate the vegetable oil in order to produce solid fats that increase the oxidation stability of the vegetable oils, but at the same time increase the melting temperature at quite high numbers. But since 1911, we know that restricting the hydrogen of this in this reaction, in this hydrogenation reaction, we can achieve a partial hydrogenation of the unsaturations present in the fatty acids of the triglycerides in the vegetable oil, resulting in a partial hydrogenation of these double bonds, but at the same time in some isomerization of the native cis double bonds present in the fatty acids. As a result, the fats that are obtained are not as hard as when we achieve full hydrogenation, and we obtain plastic fats with a mild melting temperature that are very useful to develop new kind of products, because they provide the solid fat content and the change in the solid fat content as a function of temperature to achieve very exciting functional properties associated with the melting temperature of the product. And since the use of this partial hydrogenation in the processing of vegetable oils, new different kinds of new products were introduced in the market, and they were very well accepted by the consumer. But they expose the consumer with new and exciting textures, with new kind of products. And also, let me say that the regulatory agencies like the FDA, they were very happy during the early time that these products were introduced, because they provide the consumer with a healthy choice of a fat. because they were produced from unsaturated fatty acids. They were very healthy, as believed in that time. And it had to pass about 10 to 15 years since their introduction until during the mid 1950s, some studies reported in the scientific literature link the consumption of trans fatty acid with cardiovascular disease. Uh, this has to overcome the use of trans fatty acids in different products. This is just some examples of the products that have high concentration of trans fatty acids, and you can see that there are a lot of products, and these are just some examples, and they provide very nice textures. They are very stable to oxidation, and I'm pretty sure that you are addicted to some of these products still in the marketplace. But nowadays, there is enough evidence that it strongly links the consumption of trans fats with an increase in the risk for cardiovascular disease, even above the risk associated to the consumption of saturated fats. Studies done through meta-analysis have been established that replacing 2% of energy from trans fatty acids with energy provided by mono or polyunsaturated fats, this decreases the risk for cardiovascular disease in about 50%. Additional studies have also shown that there is a strong relationship between the intake of diets rich in trans fatty acids and the development of what is called the metabolic syndrome, a clinical condition that involves increased in blood pressure, excess of body fat, abnormal cholesterol and triglyceride levels, and the development of type 2 diabetes. Since heart disease, stroke, and obesity, as well as the development of the metabolic syndrome, are considered between the top 10 public health problems worldwide, the consumption of trans fatty acids has been in the eye of the regulatory agencies. Unfortunately, getting rid of partially hydrogenated vegetable oils, which has a high concentration of trans fatty acid, is not that easy, mainly because the use of these kind of vegetable oils is cheaper, and they provide products with a very stable oxidation. They are very stable to oxidation. Of course, with higher oxidation stability than their alternative free of trans fatty acids. In addition to that, the temperatures for crystallization are achieved at higher temperatures, and therefore they have higher crystallization rate in comparison with the trans-free alternatives. So it's easier to achieve crystallization product with the use of trans fats, and they result in products with very good plasticity, very good texture profile, and they are, as I already said, very stable to oxidation, in contrary to what we obtain with the trans-free alternatives. And the main problem with this is that all the technology involved in the production of lipid-based food products were supported by the use of trans fatty acid, particularly with the phase transition associated with the trans fats. Anyway, the negative effects that link the consumption of trans fat with the increase in cardiovascular disease and with the development of the metabolic syndrome results in that different regulatory agencies worldwide start restricting the consumption of trans fatty acids through very strict regulations. And in fact, they decided to ban the use of partially hydrogenated fats in different extents. For instance, Denmark limited their use since 2003 to 2% in fats and oils destined for human consumption. But this limitation is not a restriction in the final product, but in the ingredients that are used in the final product. So this is actually a ban for the hydrogenated fats, the reuse of the hydrogenated fats. The same happened in Switzerland, more recently in Canada, and the country that most delay the assumption of this regulation was the United States. Until very recently, the United States did not recognize the use of trans fat as GRAS products. So officially in 2018, the FDA banned the use of hydrogenated fatty acids in all foods sold in American restaurants and grocery stores. Within this context, the challenge for the food industry is to develop food products that fulfill the functional properties and at the same time provide the health benefits demanded by the consumer. Several of these health demands that the consumer has are associated with the consumption of unsaturated oils from vegetable and in some cases marine sources. Evidently, these foods have to provide the requirement for polyunsaturated fatty acid essential for the human metabolism, particularly for cell membrane structure and function, and also necessary for the synthesis of metabolites necessary for the regulations of the blood flow that limit the risk for cardiovascular diseases. We also require the polyunsaturated fatty acid for the correct brain development in infants and are involved in anti-inflammatory processes in adults, limiting the development of arthritis and Alzheimer's disease. So, structuring unsaturated oil is essential to provide the functional properties associated to the sulfates provided normally by the saturated and trans fatty acid. So the technological potential of molecular self-assembly resides in increasing the nutritional profile of foods by replacing the solid fat by structured unsaturated and polyunsaturated oils, but with limited or no effect in the functional properties of the food product. And actually, this is the real challenge because it's not easy to get rid of the functional properties provided by the trans and saturated fat and replace them with liquid vegetable oils without affecting the functional properties of the product. So now we are trying to introduce the use of self-assembly as a tool to achieve this, to provide a structure to the vegetable oil. And in a general sense, self-assembly is the spontaneous association of different types of individual units of material that are in a melt or in solution and develop a very well organized, defined structure. This without the external introduction of forces that provide this assembly. That's why the definition of molecular self-assembly is associated with a spontaneous assembly of these molecular units. And these molecular units are in different areas. And probably you are not aware that molecular self-assembly is associated with the development of biomembranes. where the phospholipids are some molecules that self-assemble and develop these biomembranes, and also with the folding of proteins. Due to the molecular self-assembly, the proteins fold in particular ways that provide it with functional properties required by our organism. Also, the development of liquid crystals that respond to impulses, electrical impulses, and provide us with information storage or the display of certain type of images are associated with self-assembly. The folding of the DNA is also associated with the particular properties of the nitrogenous bases that are capable of self-assembly and develop this particular structure that stores the genetic information in our organisms. But in addition to that, lipids and amphipathic molecules are very well recognized that go through molecular self-assembly, and they are used to develop new kind of structures that have been under study during the last 15 to 20 years. The self-assembly can be classified by the size, nature of the building unit, and the kind of structures that we are interested in using in a structure vegetable oil is the one that are in the range between 1 nanometer up to 100 nanometers. But this molecular self-assembly can increase in size through agglomeration of the initial stages of the molecular self-assembly and develop colloidal structures that are the actual structure that provide the solid kind of behavior to these systems. So now we are going to talk about the oleogels. The oleogels are the results of self-assembly of particular gelator molecules that have very low molecular weight, lower than 3,000 Daltons, and these molecules can self-assemble when we use as a solvent edible oils. So different kinds of edible oils can get structured through the molecular self-assembly of low molecular weight molecules. And these molecules can be in the neat state, like phospholipids, some fatty acids, different kind of N-alkanes, also monoglycerides. In some other cases, we can prepare mixtures of these complex and provide a better molecular self-assembly that might structure the oil at very low concentrations. And within these kinds of man-made gelator mixtures, we have a mixture of 40% sitosterol and 60% of ethanol, and also a mixture of ethyl cellulose and monoglycerides. But in other cases, these mixtures of gelator molecules are native to us. So they are found in the nature, like complex mixtures of vegetable waxes, and among them we have the rice bran wax, the candelilla wax, and the sunflower wax that are now currently used in the development of oleogels using vegetable oils as the organic solvent. And in these cases, the thermodynamic force that drives the molecular self-assembly is what we call the supercooling or the supersaturation, which is the decrease in temperature, below the solubility temperature of the gelator molecules. And through this thermodynamic force, we can achieve molecular self-assembly that is stabilized through very weak, short-range, reversible intermolecular forces that stabilize these very exciting kind of structures and develop three-dimensional structures that we call supramolecular structures. And they form interweaving plates, fibers, ribbons, or hollow cylinders that physically trap large amounts of the oil through capillary forces. Fortunately, these short-range forces are reversible, so we can form this gel, this oleogel, and then heat the oleogel, melt it, and if we cool it back, we are going to obtain exactly the same kind of gel that we have at the very early stages. So these kind of forces, fortunately, are thermoreversible forces. They are very weak. No covalent bonds are involved in the development of these kind of gels. And because of that, we have now a new system that has thermal and mechanical properties completely different from the ones that are observed in the individual components. That we have a vegetable oil and we have a gelator, which is a solid. And when we mix at a particular concentration, we heat them and then we cool them below the solubility temperature of the gelator in the solvent. We achieve gels that are thermoreversible, elastic, thixotropic, and have a high oil binding capacity. And by high, I mean that probably a concentration of 0.1% or even lower of the gelator molecule in the vegetable oil can achieve gelation of 90-95% of the vegetable oil present in the solution. There is a limitation of this because the gelator self-assembly capacity and the temperature for phase changes, because this involves a phase change from liquid to solid, and also the topology of the supramolecular structure are solvent dependent. That means that if we change the solvent, the conditions to achieve gelation completely changes, and probably they are not achieved as in the original solvent in which we develop the conditions in which we achieve gelation. So we have to understand all these different factors that affect the development of molecular self-assembly in order to introduce this new kind of technology and the development of a new generation of fats. What we have is that if we have a solution of a gelator, which is at the very top, and we start decreasing the temperature, then we are going to achieve a certain extent the molecular self-assembly. And if we continue decreasing the temperature, we are going to develop the supramolecular structure that provides the correct gelation and the development of oleogels. But if the interactions between the gelator molecules are higher than the interaction between the gelator molecules and the solvent, then we are going to achieve precipitation, insolubility of the gelator, and therefore no gelling conditions are achieved. In the same way, if we have a higher extent of a relationship between the gelator and the solvent, then we don't achieve a particular extent of gelator interactions, and we achieve full solubility of the compounds, and again, no gelation conditions can be achieved. So the achievement of gelation requires a balance between the contrasting parameters associated to the gelator and gelator solvent molecular interactions. And achieving molecules that can develop oleogels under these conditions is not an easy task. In most cases, the gelator molecules that are capable of developing oleogels have been found by serendipity other than through a systematic approach. And we wanted to change that. Different groups worldwide are trying to understand what are the different conditions that provide us to achieve the development of this kind of non-traditional lipid structuring through the use of low molecular weight chelators at concentration as low as 2% or even lower through the use of chelator molecules in order to mimic the development of a structure achieved by the traditional self-assembly of triglycerides. These triglycerides that are developed through cooling too, but they develop spherulites that are agglomerated and they start immobilizing the vegetable oils, but they require concentration as high as 30%, provided a system with high concentration of saturated and trans fatty acids to provide the functional properties required in food systems. And we can see here the final structures achieved by the traditional fat crystallization using triglycerides high in saturated and trans fatty acids that require the use of 30% of solids, and the kind of gel structure that can be achieved by the non-traditional way of achieving the gelation of the vegetable oil through the use of low molecular weight gelators that require in this case just 2% of solids, and we can develop this kind of a structure which contains 95% of unsaturated fatty acids. This is the kind of the systems that we want to develop and use them to formulate new kind of products that provide the consumer with a healthier food products than the one developed by the traditional approach that requires the use of trans and saturated fatty acids. And in order to do that, we are using an approach that we are calling the microengineering of molecular self-assembly that basically recognizes that there are two different kind of variables that affect the phase transition, the development of crystals, the topology of the crystal network, and the solid to liquid phase ratio that are required to obtain the functional properties in the oleogel, the physical properties required to achieve the functional properties in the food product. So these variables are the chemical variables, which are associated with the chemical structure and the concentration of the gelator, with the addition of some components that might help to the molecular self-assembly. And also we have some physical variables. These physical variables that are external forces that are applied during the self-assembly, and this mainly involves the use of shearing and cooling rate. We have been using this model in order to understand the factors that determine the molecular self-assembly of different kind of molecules developed in the lab in order to achieve oleogels with particular physical properties that provide us with functional properties in food systems. And for this, we have been using what we call the bottom-up approach, which is starting with a very well-defined molecular architecture, and from there start building, modifying this molecular structure. And then these small changes, these small but systematic modifications in the basic molecular structure, then are used to develop oleogels. And then we measure the gelation capacity, the microstructure of this organization, and the physical properties of the gel. And once these results are obtained, we have the basis to do additional changes in the original molecular model, and then those changes are now once again measured in the development of new gels to see their effect and start understanding the effect of changing particular structures in the basic molecular model and understanding what are the main characteristics that define a good gelator. And from this, we have been working with our partners in Washington University, particularly in Georgetown University. And we have been using as our basic molecular structural platforms 2 molecules. One is the stearic acid, which is an edible molecule used in different kind of products, but this stearic acid is more used in cosmetic products, particularly in products that require spreadability on the skin. And we're also using a very close molecule for stearic acid, which is the 12-hydroxystearic acid, which differs from the stearic acid in that has an oxidryl in the carbon number 12. And as you can see from the very beginning, stearic acid can achieve this kind of crystal structures that immobilize the oil, that provide very weak gels. But just the change in one oxidryl in the structure provides us a different kind of crystal organization in fibers, and these structures increases the gelation capability of the molecule. In order to observe this in a better way, we are using rheology measurements, particularly elasticity and yield stress. And we are also observing the changes that we are going to do in these molecules in the microstructure developed in the vegetable oils. And in this case, the vegetable oil that we used was high oleic vegetable oil. And we use polarized light microscopy to observe the microstructure. And in here, we start by observing that we develop 2% oleogels of stearic acid using a cooling rate of 1 Celsius per minute until we achieve from 90 Celsius degree down to 25 Celsius degree a particular gel, a gel that then is maintained under isothermal conditions during 60 minutes, and during that time, we measure the elasticity of the gel and at the same time, the yield stress. As an additional measurement, we also evaluate the content of solids in the gel developed by the stearic acid. And as you can see, these provide a very, very weak gel, but still a gel. And then when we introduce an amine group as a functional group in the very same kind of molecule, but now we increase the capability of developing hydrogen bonds with other molecules, we can achieve a higher elasticity. This higher elasticity was completely associated to increasing the capability of this molecule to develop hydrogen bonds. Not only the elasticity was increased, but also the resistance of the gel to break the yield stress. And as you can see, the microstructure of these molecules completely different to the previously obtained. And then if we use the hydroxystearic acid that has an hydroxyl group in a chiral carbon, then we again increase the elasticity of the gel obtained. Not only the elasticity, but also the strength of the gel. In this case, the amount of solid developed by the hydroxystearic acid increases drastically up to a level of 1.5%, but still with this concentration of solid, we can achieve a very nice and a strong gel. If now in this molecule we introduce again an amine group, then we once again increase the capability of this molecule to develop hydrogen bonds. Now the structure is very fibrillar, and we increase drastically the yield stress of the gel obtained, and also the elasticity of the gel. If we keep doing these changes, but now increasing the capability of developing van der Waals forces, introducing a propyl alkane side change to this molecule, the increase in elasticity is very drastic. And also, we can see a drastic change in the way these molecules crystallize. Now we are developing spherulites, fibrillar spherulites that can interpenetrate one sphere, the fibers can interpenetrate one spherulite into the other, increasing very dramatically the elasticity of the product, of the gel actually, and also the yield stress of the gel obtained. If we now increase the length of the alkyl group introduced to the molecule, then we achieve a very high elasticity of the gel obtained. The yield stress has also increased, and these characteristics of the gel are achieved with just 0.8% of solids present in the system. The microstructure of the gel obtained is fibrillar. There are interconnections between these fibers, and this provides us the basis to start theorizing that we might develop products that can achieve the texture of margarine developed by solid fat with high content of saturated and trans fatty acid that require 20 or even up to 40% of this fat to achieve elasticity similar to the one that we are achieving with this molecule, with using just 2% of gelator in solution. At the same time, if we compare these results obtained with these molecules with the rheological properties, for instance, animal protein-based hydrogel made with 10% gelatin, we obtain values very close to the yield stress achieved by this molecule with just 2% of the gelator in solution. So we are now in a new field in which we can start mimicking the properties of the structure developed by the saturated and trans fats with molecules that might be synthesized, and probably some of them might be even present in different kinds of native products, and we just have to recognize them and use them in the development of this new type of fats. We continue doing some additional experiments with these kind of molecules, and now we try to see the effect of mass and energy in the rheology of the oleogel. And we can see here that using this molecule that achieve this particular gelation capacity, just by increasing the cooling rate to achieve the same gelation temperature, now we can increase the elasticity of the gel obtained, and we achieve thixotropic properties. But if we apply exactly the same kind of cooling rate to a different kind of molecule, now we obtain the opposite changes. So this just presents you the need to understand more what is happening. And here we explain this behavior very easily, because the increase in cooling rate decreases the size of the spherulites obtained, and therefore the capability of interpenetration between the fibers has been decreased. As a result, the elasticity of the gel decreases. We now know that we can develop junction zones in these fibrillar structures, and the relation between the transient junction zones between the fibers and the permanent junction zones between the fibers determine the rheological properties of these systems. And for this, to evaluate this, we have been using different cooling rates applied in two different stages of the development of the oleogels. One cooling rate before achieving the melting temperature of the oleogel, and then continue the cooling rate under static conditions until achieving the gel setting temperature. And we have been using under these conditions two different cooling rates, 10 Celsius degree per minute and 1 Celsius degrees per minute. And in order to evaluate the effect of these in the gelation properties, we are using this kind of rheometer in order to develop the gel between the geometry of the rheometer, and then at the end measure the elasticity. And as you can see here, the use of a different cooling rate provides us with better rheological properties when we use higher cooling rate. We have continued our experiments now using two different kind of temperatures during the same process of achieving the gel, of developing the gel, one using first 1 Celsius degrees per minute during shearing, and then continue the gelation under static conditions using a cooling rate of 10 Celsius degrees per minute. And right here we use the opposite. And we measure the changes, and with this, we achieve even higher gelation properties, higher elastic properties in the gel. And unfortunately for us, this kind of effect, this effect of the variables of cooling rate have also been observed in different kind of molecules that have different molecular weights, but particularly we see that the alignment of the molecules are more easily to achieve in molecules with higher molecular weight, because they can extend the conformation during the cooling of the molecules and the applying of the shearing, and develop gels with higher elastic values, with molecules with lower molecular weights that don't have the possibility of keep the extended structure to develop a very well structured gelling that retain the vegetable oil. So the major effects derived from these studies is that gelator molecules can go through a shear-induced molecular alignment as a function, one, the molecular weight of the gelator molecule, and the cooling rate applied at temperatures before achieving supercooling conditions. And also, we know that these conditions depend on the gelator molecule, but there is a particular condition that we can achieve oleogels with the highest elasticity in comparison with the oleogels developed under static conditions. Fortunately for us, the same kind of conditions, the same kind of results are achieved when we use as gelator molecules Candelilla wax, which is a vegetable wax obtained from a shrub from the semi-desert of Mexico. We can achieve very nice gels applying exactly the same conditions that we obtain from our molecular models. And now the vegetable waxes are actually the less expensive gelator molecules that we can use to develop oleogels. These waxes are multi-components. They have different components, but in most of the cases, one particular component is the one that provides the self-assembled properties to these waxes. Here, carnauba has a very high concentration of long chain esters. Candelilla wax has a very high concentration of alkanes. Rice, hull, wax, and sunflower wax have very high concentration of long chain esters. These waxes have very high gelling capacity. They are food grade, they are economical, and the availability is worldwide, and they are compatible with other food components. They provide different kind of structures that can trap vegetable oil at concentration as low as 0.5% in the case of rice bran wax, or 0.75% in the case of candelilla wax. So now we can develop margarines with oleogel concentrations that allow us to reduce the concentration of saturated fats in these margarines to levels as low as 13%, 12%. So we can develop new kind of products by mixing hydrogenated soybean oil with oleogels developed, for instance, by sunflower waxes. And in that way, decreasing the content of the saturated fats in the final product. Nowadays, the use of edible oleogels in different kind of products is a reality. We can use this kind of oleogels in the development of baking products, different kind of baking products in the development of different kind of margarines, even use these new edible oleogels in the development of new formulations of community meat systems. And the content of the very healthy vegetable oil is very high in these kind of products. There are also new approaches for oil structures in addition to oleogels. Now we can use the emulsion as a template to develop new kinds of vegetable oils. We can use different systems, what we call structured biphasic systems, in order to develop structured emulsions that provide us with new kind of lipids, new kind of fats. And the success in the development of this new generation of edible and healthy fats using these novel approaches to structure vegetable, and in some cases marine oils, depend on the capacity of these new fats in deliver the functional and nutritional properties required by the consumer. Within this context, as new products using this new generation of edible fats are currently introduced in the market, the consumer will have to evolve in their food choices in a similar way as when the products developed with trans fats were introduced, and they have to compete now in the market with the traditional products elaborated with saturated fats, with the additional value that the products developed with this new generation of fats are with higher nutritional value. Thank you very much for your time, and if you have questions, I am available.
Thank you so much, Dr. Toro, for your very nice presentation. And now, if you are able to make your question to our speaker, you can open your microphone, or you can also write it in the chat so I can read it out loud. So let me open microphones. Anyone with a question? Okay, so I have one from, if you want, Andres, you can ask it, please. Andres is my student, so I hope he has good
Okay.
questions. Go ahead,
Okay, go
Andres.
ahead.
Yes, I am actually in the lab right now, and I have multiple questions. The first
What
one,
are you doing there?
oleogels, actually. The first one will be that are these modified or enhanced oleogelators highly efficient with mono or polyunsaturated
Yes,
oils?
yes. We always use highly unsaturated vegetable oils as the solvent, and we obtain a very high gelation capacity of these from these gelator molecules, as high as using probably less than 1% and achieve the full gelation of the vegetable oil.
Thank you. And does these natural waxes alter the mouthfeel compared
Oh,
to
yes,
synthetic?
one of the limitations of using vegetable waxes are that they impart a waxy flavor. That's why when you blend the oleogel obtained with the use of vegetable waxes, when you blend them with some other fat, let's say that you now have a mixture of or a formulation made with 80% oleogel and 20% of saturated fat, you can hide the waxy flavor and use and develop new kind of margarines, for instance, or shortenings.
Yes, of course, the texture depends on the application that will
Yes,
be given, right?
of course.
And finally, just to close, can the cooling rates be, uh, well, like forgiven, and then can the oleogel be taken at room temperature?
I'm sorry, I didn't get your question. The cooling rate, what?
Be like forgiven or set aside, and you can let the
Ah,
oscillators
yes,
at room temperature?
yes. I present you with these cooling rate effects because it's very nice to measure the effect of cooling rate in the gelation properties of the oleogel obtained. But if you allow the system to cool at room temperature and then measure the gelation properties, that is also fine. But unfortunately, you won't have ways to measure the possible effect of cooling rate in the gelation properties of your system. And if today, like for instance, you are in Monterrey or Querétaro, I don't know, as today is a very hot day, it's going to take forever to achieve room temperature. If the next day is a very cool day, then achieving room temperature is going to take less time and you are going to obtain gels with different properties. And you won't be able to figure out why the difference in gelation property. That's why it's advisable to control the cooling rate in order to maintain the quality of the gel under very repeatable conditions.
Thank you.
You're welcome.
I have another question,
Thank you.
if
Go
I may
ahead.
ask. Well, you said, for example, uh, that specific changes can be done on molecules, right, for research on specific properties.
Yes.
So, how do you like program these specific changes in one molecule? Like, if you say, for example, I want to get rid of this insaturation particularly and not every insaturation in the molecule,
Okay.
or I want to remove like
That's why
this
that
kind of
when you work in this area and you are synthesizing molecules and trying to see what are the changes that produce a particular effect in the oleogel that you develop, it's very advisable that you work with very good chemists. The chemists know how to produce those changes and develop new kind of molecules. And probably they are not, they don't have the knowledge of how to measure the effect of those changes in the oleogel that you obtain. So you have to form a kind of a multidisciplinary group in order to work in this area. One that is very knowledgeable of the on how to do those changes in particular molecules. Another group that is very knowledgeable on how to measure those changes in particular kinds of oleogels. I don't know
Thank
if
you.
that answered your questions.
Yes. Yeah, I think it's pretty much about the team you have, right?
In other cases, what you do is to work with a native component. Let's say you extract alkanes from the candelilla, and you see what is the effect of extracting those alkanes from the candelilla in the candelilla capacity of developing particular gels, and then you start figuring out how they interact in the candelilla to achieve this and that oleogel.
Mhm. Thank you.
Welcome.
Thank you, Daniel. We have time for perhaps one more question. So I'll make it if it's okay with you. Have
Okay, go
you
ahead.
have you tried any nutraceutical compounds like encapsulated or integrated in the structure of the oleogels?
Yes, actually, that has been the work of a couple of patents with some cosmetic industry, and the products are already in the market, and we have been able to encapsulate particular active systems that are used to control the development of herpes, the development of blisters on the skin, and in some other cases, we have been also able to encapsulate capsaicin in order to use it as an active agent for particular diseases that I am not aware of, but just working in encapsulated capsaicin. So it's very easily to do it. The main encapsulating the active compound is very easy. Maintain it stable is a challenge, because in some cases the oleogel is disrupted by the presence of the active compound. The stability of the oleogel is reduced quite drastically, so you have to work in the stability of the product.
I think someone, thank you, Dr. Toro. I think my connection sort of failed. Thank you
Okay.
for your answer. And can I make a last question from Javier from the audience? Is that okay with you?
Yes, go ahead.
He says, how do you categorize the gel properties of certain molecule? Is there any rules to find them, or is it by try and error?
Well, actually, what we do is we always try to compare the gelation properties of the oleogel that we are developing with a product that is already in the market, or a model that is already in the market. That's why we compare the gelation properties of the molecules that we develop with the rheological properties existing in a very hard butter, in a spreadable butter, and in a gelatin. So we can see how far, how close we are to the gelation properties that we want to achieve. I think that's the best way of doing it, because you have to to have at least something to compare with. Otherwise, you are just developing oleogels and you don't know where you are standing. Oh, let me say hello to my dear
Yes, now I
friend,
have.
Mariana. Hi, Mariana.
Hello, Professor. How are you?
I don't have coronavirus. You can get rid of your mask.
Yeah, no, I'm in the laboratory. So
Okay.
thanks for your presentation.
Very nice to see you, Mariana.
You too.
So, do you
We
have another question?
Yes, I actually have a couple of them, if it's okay
Okay,
with
go
you.
ahead.
One is from Mayela Garcia. What are the most important factors to consider in organogels for use on industrial scale? And we also have from Guillermina del Campo, which I know her because she's in Ragasa. Would you recommend adding lipovitamins to the oleogels?
Adding what? Sorry?
Lipovitamins.
Lipovitamins. Oh, yes. Well, to answer the first question, which chapter I don't recall now. What was the first question?
What are
Sorry.
the most important factors to consider in organogels for use on an
Okay,
industrial scale?
If you are going to use it at the industrial scale, you have to look for gels that are available under a constant through the year, because you are going to produce them through the year. They have to be economic, with economic value. They don't have to be toxic. They have to be approved by the regulatory agencies like the FDA. And they have to provide you consistent properties in the oleogels. One of the main problem of the vegetable waxes is that the oleogels that you obtain from vegetable waxes vary from batch to batch. So you have to understand how to keep them constant. And I think those are the main variables that you have to look in when you are developing oleogels. And to answer the question of Guillermina, yes, you can add lipid soluble compounds. Actually, it's very easy to do it, as long as the concentration of those lipid soluble products don't affect the solubility of the gelator in the vegetable oil, then you can add it very easily. Because in some cases, as I mentioned in my presentation, a drastic change in the solvent used to develop the oleogel changed completely the way you obtain the oleogel, because the way they self-assemble and how they develop the macrostructure are solvent dependent. Okay.
Thank you so much, Dr. Toro, for your presentation. Thank you for your time. Thank you for sharing your knowledge with us. And thank you everybody for participating in this webinar. Please keep tuned and check our website and Facebook page. And we also have an Instagram account and LinkedIn for more information regarding to our next webinar. Hopefully we'll have a last one during this year in November. And again, muchas gracias, Dr. Toro. Thank you, everybody.
Thanks to you.